Welcome to qnawire.
This is Chapter 22, Problem 14 from Sears and Zemansky's University Physics. A solid metal sphere with radius 0.450 meters carries a net charge of 0.250 nanocoulombs. Find the magnitude of electric field A at a point 0.100 meters outside the surface of the sphere, and B at a point inside the sphere, 0.100 meters below the surface. All right, the first thing I've done is I have drawn a model of the sphere. So we're given that the radius of the sphere is 0.450 meters, which I've denoted with capital R for the radius. And then I'm looking at some distance, 0.100 meters, outside of the sphere, represented by D for that distance. And we're given that the total charge is 0.250 nanocoulombs. But that's the same thing as 0.250 times 10 to the negative 9 coulombs. So I just substituted in for nano, so that way I'm in standard SI units. And the basic way of solving this expression is to use the equation that's the definition for the electric field due to a point particle, kq over r squared. K is our electrostatic constant, 8.99 times 10 to the 9 Newton meter squared per coulomb from Coulomb's law. Q is going to be the total charge, that total charge of the sphere. Well, as I just said, we were given that. And lowercase r is the distance from the center. So we can assume, since we're outside of the sphere, we can model this as if the entire charge of the sphere was concentrated at the center. So that means the total distance from the center of the sphere is simply the radius of the sphere, capital R, plus the distance away from the sphere, d. So our distance away, little r, is the same thing as big R plus d. So I've made this substitution into the expression. And then I've just plugged in the numbers. So the constant k, plug that in. And then plug in the charge of the sphere, plug that in. And then plug in the numbers we're given for the radius of the sphere and the distance away from the sphere. And then we just enter this into the calculator. And we get that the electric field at the point that we're interested in is 7.43 newtons per coulomb. And that is part A of the problem. Part B is we want to know inside the sphere. So as I've modeled here, we're going inside the sphere. However, we know that the sphere is metal. Metal is a conductor, and because it's a conductor, all of the charges on the metal sphere are going to be on the very surface. Because if it doesn't matter if it's all positive charges or all negative charges, all the charges push each other as far away as possible, so they all get pushed towards the surface of the conductor. So if we're assuming we have electrostatics, the charges aren't moving. Therefore, inside this sphere right here, inside the surface, there are no charges in here. So by Gauss's law, if there's no charges enclosed, then the electric field at the surface must be equal to 0. So the electric field is 0 inside of the metal conductor. And all metal objects are going to have this exact same phenomenon. So E equals 0, there is no electric field inside of the conductor.